All right, as we get ready to wrap up these final few lessons of Chapter 4, we are going to be putting our models that we were working on before in motion. So in other words, remember last time we had the rectangle under the parabola, perhaps, okay? So now let's take the corners of those rectangles and let's slide them around the arch so the rectangle is changing shape so that it's growing in height and width as we move it or shrinking, okay? We're going to be moving things. Things are going to be in motion. So we're going to be adding time as an element of a variable that we'll be working with. We can't control time. Okay, time is just going to march on without us being able to control it, but we're going to at least start the timer and see what's happening to some of these things as they move. Okay, so that's called a related rate. A rate is something that's in motion, it's active, it's moving, but everything is related to each other. It's connected to each other. As the height gets wider, maybe the base gets narrower, or the height gets taller, base gets narrower. Things are all moving in motion. That's called a related rate. So we're going to look at how all those things are related to each other. All right, so that's the idea. Introducing time, developing a model that relates multiple variables to each other, and how they are connected. So our derivatives now, because we are introducing time, it's going to look a little different. This was our original derivative as we moved for something. We were taking the derivative of how y changes when we would say with respect to x. We're no longer doing that. We are now doing the derivative as y changes with respect to time. And then there will be one for the base, dB dt, maybe one for the height, dh dt, dw dt, dv dt for the volume. It's all going to be relative to time. So time is what puts things in motion. Let me show you what I mean. So you start with something with geometric in nature that's stagnant. It's not moving. So let me give you an example of a volume. So the volume of a sphere, anybody know that one off the top of your head? 4/3 pi r cubed. Okay, very good. So that is just a sphere that's just not moving. All right, so suppose we start pumping air into this sphere. So now now the sphere is growing larger. So we've now put the sphere in motion. And so that is going to be dv dt as we put this in motion. So we're going to take dv dt, and then we take our derivative. Okay, derivative rules are still the same. So we'll pull the 3 down to the front. Okay, and so we'll have 4 pi r, what's the new power on r? Squared. And then what you got to remember is that there's a chain rule applied to this because there are implied parentheses around this variable r. The variable r is still changing, and so we'll be multiplying this by dr dt. All right, and that's it. For now, I mean, that's the idea, is that you start by putting something in motion by taking the derivative and remembering that there has to be a dt on both sides of the equation. There has to be a dt on the volume side, and there needs to be a dt on the radius side as well, because the radius is moving while the volume is moving. If the volume, you can't change the volume without changing the radius at the same time. All right, how about surface area of a sphere? The formula for the surface area of a sphere. Okay, anybody have that one? Okay. Do you see that anywhere? Interesting. Where do you see 4 pi r squared? Uh-huh. Mm-hmm. Isn't that cool how that works? All right, but if we want to take the derivative of that, we want to put the surface area. Clearly, if we're pumping air into this, the surface area is growing as well. And so then we'll have ds dt. So this is the rate, and it is related to the derivative, so that would be 8 pi r, and then times dr dt as well. All right, you cannot, these rates are related to each other. I can't have a rate for surface area without also having a rate for the radius, because as you pull the surface area bigger, you are also impacting the radius. The radius is changing at the same time. All right, how does time impact a rectangular block of ice as it starts to melt? Notice I said it was rectangular. I did not say it was cubic. This is a rectangular block of ice. So the rectangular block of ice means it has distinct length and width and height. That none of those things are necessarily the same. If I wanted some of them to be the same, I would have said where the base was a square. Or if I wanted it to be a cube, we'd say all the dimensions are the same, but not. So how does time, if we want to have this melt, clearly the volume is going to be changing as this thing is melting. So we'll have dv dt. What rule will I need on the other side? I'll need the product rule. Okay. If we had just L and W, we know what the product rule would be. So imagine if you just had L times W, then we know that the product rule is W times dL dt plus L times dW dt. We know that already. Okay, that's our basic product rule. If we've got triple, then it's just all the combinations. You've got one derivative at a time. So if you have 3 of them, then it's going to be, we'll start with H and W, and then the one that would be derivative would be the L. Doesn't really matter the order because these are all multiplication. So H times W times DL. Then maybe we could do H times L times dW. And then what else? What's the one I'm missing? Okay, L times W, and then the rate I'm missing is dH. So that's the product rule. If you had 3 different variables, it's one rate at a time, and then the other ones remain unchanged. Okay, so if I had 4 of them, then it would be 3 variables and 1 rate, and just all the combinations you could do. Yeah?
Can you clarify why you put the H in front?
There's no reason. I could have just as easily put the W in the front. Multiplication is commutative, so it doesn't matter what order. Okay. All right, what if I was doing surface area? I did notice that surface area on the wrapping paper question on the quiz was something you guys struggled with a little bit. If you have something that's a rectangle, how many surfaces are there that you have to cover?
6.
There are 6. So you need to express all 6 surfaces. And so there would be, one of the surfaces would be L times W, and then another one of the surfaces would be W times H, and then another one of the surfaces would be W times H, and then that's 3 of the surfaces. But then each of those are repeated twice because they have their counterpart on the opposite side. So this is the surface area. There are 2 lengths and widths, that's the top and the bottom. There are 2 widths and heights, those are the 2 sides. And there are 2, whoops, what did I did 2 the same. Which one am I missing? WL, WH, LW. And I have 2 lengths and heights, that's the top and the bottom. So you've got 2 of everything. Now, if you want to put that in motion, then your derivative is going to be applied to each of those. So I'm going to have 3 mini product rules all going on at the same time. Okay, 3 of them. So I'll have 2 times, and then there will be a product rule. So W dL dt plus L dW dt. That's the first product rule. And then 2 times in the next product rule, I'll have H dW dt plus W dH dt. And then the last product rule would be H dL dt and L dH dt. All right, so that is, so we're just working on how this works. So these are the related rates. The rate of the surface area is related to all the other rates, the rate of the height and the rate of the width and the rate of the length. They're all related in rates. Any questions so far? Okay, we get to start putting numbers in, of course, but. Okay, so here's our first number. Consider a soap bubble, and it's perfectly spherical, and we're gonna blow air into this. So this is the same thing we saw. You always start with your geometry, 4/3 pi r cubed. I expect you to know that. Move on to your calculus, which is taking the derivative, pumping air in so that you're changing the volume. So 4 pi r squared, and then times the related rate of dr dt. All right, then we start putting numbers in. Now the number 10, I want you to look at what the units are associated with the number 10 so that you know where the right place is to put it in. Okay, the clue is always in the units. So if I'm looking at these units, I have cubic centimeters, which is measuring volume, over seconds, which is measuring time. So I have something where there's volume over time, and the only place that exists is right here. That's volume over time. So that's where I'll put my rate. I'll put 10 here. I'm not given anything for R at the moment, so that's the only number I can put in. Now I'm gonna have to make sure I answer the question. And the question is, how fast will the radius be changing? In other words, what is the rate for the radius? And so that question will be answered by dr dt. Okay, how fast is always a speed, okay, or a velocity. And so I'll be looking for that, which means I just need to solve and get that alone. So I'll have 10 divided by 4 pi r squared, which when I reduce is 5 over 2 pi r squared, and that's dr dt. So dr dt by itself is the reducing of 10 over 4. The last thing you're reminded is answering in units. Again, your clue for units is always what is the unit for the numerator and what would be the unit for the denominator. So looking at my numerator, I have the rate for R, and R would be measured with what unit in this situation? Centimeters. Okay, if the volume is measured in cubic centimeters, then the radius has to be measured in centimeters, and time is still measured in seconds. So my unit is going to be centimeters per second. And every time you forget units, then you're deducted a point every time. So the units are going to be important. Sometimes they'll remind you, and sometimes they don't remind you, and you just have to remember on your own. Time, this is a rate. It's not radius is just a length, and radius is measured in centimeters. What's the only thing that's measured in square units? Area, right? And so I'm not talking about area. I'm talking about a length, right? Radius, right? The radius. Okay. All right. So let's try another one. Okay, your favorite. Back to a cylindrical tank. So a cylindrical tank has sprung a leak. If it's leaking, how fast is the water level dropping? Right, so we just need to start with the geometry of the situation. So my geometry is a cylindrical tank is pi r squared h. That is my cylindrical tank. Don't focus on the numbers until after you've done your calculus. So geometry first, set up your model, do your derivative, your calculus next, and save your numbers for the end. I see general mistakes happen when people plug in the numbers at the beginning. If you're plugging in numbers at the beginning, then when you take the derivative, everything turns out to be 0, and every answer would be 0. So you want to wait until after you've done your derivative. So we'll take dv dt. Okay, what rule will I need to take my derivative here? I've got a pi times an r squared times an h. Product rule. Okay, is this a double product rule or a triple product rule? Why? Why not 3? Because I do see 3, I see a pi and an r and an h. Pi is a constant, okay? So I could use it. It's not gonna, you wouldn't get the wrong answer, but you don't need to. Pi would be a constant. And so then I'm gonna take the derivative now using my product rule. So I'll start with h, and then I'll take the derivative of r squared. The derivative of r squared is 2r times dr dt. Don't forget the dr dt. When you're working with the derivative of r squared with respect to time is not just 2r anymore. The derivative of r squared with respect to time is 2r times dr dt. And then plus, and then we'll have r squared times dh dt. Now I can look to plugging in values. And so I was given some values. I was given 0.03. The units are liters over time, which means I'm going to be plugging that in where my volume is being measured over time. So this unit here, actually, we'll use the milliliters one, okay, is going to get plugged in for my volume. So that'll be 30. There's other clues, though. I need to be sensitive to actually what's going on. This word leaks isn't going to be important because my volume is changing in what kind of way? Yeah, my volume is getting less. The liquid that's in this is going down. So it's not just 30, but it's negative 30. Again, if you miss that, you might pick the wrong multiple choice option. Okay. Now, again, you got to be good readers. The number 30 was there clearly. The word leaking, I had to sort of infer. But then there's one other number in there that is definitely implied that is not as obvious. So I'm going to show this to you just once. Okay, so imagine you've got your tank here like this. Okay. All right, it starts out full. All right, then if I'm right here, now the level is this high. What dimension has changed? What dimension has stayed the same? The radius. Okay, and so then if I've, now the water or the liquid level is down to here. What dimension has changed? The height has changed. What has not changed? The radius. Okay, and then if I'm down here, now the level is this high. Okay. The height continues to change while the radius continues to stay the same. Since the radius stays the same, dr dt is the rate at which the radius is changing. Is the radius changing? No. So what's the rate at which the radius is changing? 0. That is implied by the shape that you're working with. So I do have one other number I can plug in, and that would be the 0 for the dr dt, because the dr dt is measuring how much change is happening to the radius. And we've just established that the radius is not changing at all. Okay, what if your tank was shaped like this? Okay, and then your water level went down a little bit more. Okay, 2 things are changing now. The height changed and the radius got smaller. So you can't put dr dt as 0 for that. It's only in a cylinder shape that you could put dr dt in. Okay. All right, and then to answer the question now is asking me how fast is the water level dropping? And so that's going to be answered by the speed of dh dt, or the value of dh dt. It's that. So that's what I want to get alone. So I need to simplify this to the point where that is what is alone. So I now have negative 30 equals, the 0 is gone here, all of that multiplied by 0. So I have pi r squared times dh dt. And so if I want to get dh dt alone, it will be negative 30 over pi r squared. And then I need to remember to insert units. Yeah.
Why don't you distribute the pi to the DHT?
Because this is multiplication and this is one quantity, so you only distribute it. Let's do basic distributing. Okay, so let's say you had 2x and then you had x plus 4y and you were let's just do 2, keep it simple. What do you distribute the 2 to? You distribute it here. You don't distribute it to the 4 and the y. You only distribute it to the 4y as a quantity. So you get 2x plus 8y. That's basic distributing, multiplication.
Okay.
If there was a plus in between there, then I would distribute it to the r squared and the DHT. I'm not. All right, let's get our units on here. So again, use the clues of the numerator. The numerator is dh. What is h being measured in? H is a height. What unit do we use to measure height? Not meters in this situation. I don't see any meters. Milliliters doesn't measure height. Milliliters is a value for volume. Come on, science teachers. Come on, science teachers.
So, centimeters.
Centimeters, okay? Why centimeters?
1 milliliter.
1 milliliter is equal to a cubic centimeter. A milliliter is a measure for volume. The corresponding measurement for volume would be a cubic centimeter. And so the corresponding measure for height would be a regular centimeter. So this is in centimeters. And then I'm still looking at centimeters per second.
And we just put the unit, does it matter where we put the unit, or do you want it on the left side or right side?
Typically it would go on the left. It would go after the expression.
After now.
Uh-huh.
Oh,
Yeah, because we don't say,
Right, I'm just.
like, yeah. The answer is negative 30 over pi r squared centimeters per second. Yeah.
And how is pi r squared seconds?
Pi r squared is not seconds.
Oh.
This, it's the numerator and denominator
Oh,
of this.
right,
It's
sorry.
not the numerator and denominator of what you get, it's the numerator and denominator of what you're expressing. Okay. Because when I have a radius to plug in, I'm gonna get an actual number.
Yeah.
Okay. All right, let's try another one. Okay. A little bit different geometry now. Police officers chasing a suspect. The suspect has turned the corner, and we're assuming that the street is a right angle, okay, 90-degree street, not like Los Coyotes diagonal or something. All right, now don't get distracted by the numbers, 80 miles per hour and the distance of 20 miles per hour. Don't get distracted by that. Focus on what's going on between the police officer and the suspect. So we've got a police officer chasing a suspect. Here's your police officer. Your suspect is here, okay, around the corner. The geometry shape that comes up out of here is a triangle. In fact, it's a special kind of triangle. What kind of triangle? Okay, it is a right triangle. Okay. The geometry from a right triangle is either going to be some kind of trig, that means you're using an angle, or it's going to be Pythagorean theorem. Okay, we're not needing an angle in this question. We are asked about the distance. So we need to come up with the Pythagorean theorem. So I'm going to call this the distance between the police. So the policeman's going this way, trying to catch up to the suspect who's going that way. Okay, police is chasing the suspect. So my geometry that comes out of here is p squared plus x squared equals d squared. So when you're dealing with right triangles, either you're going to be doing trig, so katoa, or you're going to be doing Pythagorean theorem. Remember, geometry first. Set up your model first. Don't plug in the 80. Don't plug in the 20. Okay, set up your model first. Then do your derivative. Now set this in motion. So the policeman's actually moving and the suspect is actually moving. And as the police and the man and the officer and the suspect are moving, what happens to D? Okay, well, it increases for a while. Okay, so as the suspect moves over here and the policeman moves over here, now it's like this. But maybe the suspect moves over here and the policeman is here, and now it's like this. Okay, so, but what happens when the policeman finally turns the corner? Okay, now they're on the same plane, the same line now. Okay, so now the policeman can finally catch up to the suspect. All right, but we haven't gotten there yet. Let's put this in motion. All right, so I want my derivative. What's the derivative of p squared?
2p.
There we go. 2p times dp dt. It can't just be 2p anymore. 2p would mean the police officer's not moving and he's just standing still. We need the policeman to be moving. We need them to be active. So therefore, the derivative of x squared is no longer 2x, it's 2x dx dt. And then the distance is also changing, so it'll be 2d d dt. Okay, I use capital D. Now you can start dropping numbers in there. All right, the officer is going 80 miles per hour. Where does the 80 go? Okay, does it go in for P or does it go in for dp dt? Okay, the 80 is going to go in for dp dt because it is the rate. It has a miles per hour, so I'm going to put 80 here. So 2p times 80. Where does the 20 go? Okay, the distance between them. Okay, so that is d dt. So that is going to be 20. And then we have 2x dx dt, which is what's left behind. Now again, we have to infer what is going on a little bit. It doesn't explicitly come out and say. What did we say about d, the length d? Is it, let's start with x. What did we say about x? Is the length x growing or shrinking? It's growing as the x suspect is going. What are we saying about d? Is d growing or shrinking? Growing. What do we say about p? P is shrinking. And if p is shrinking, you have to put negative in here. Okay? Because the side is shrinking in size. Don't think negative like going backwards. That's not what we're talking about. It's the rate of the fact that the dimension itself will be shrinking. All right, so I have negative 160p plus 2x dx dt equals 40d. Then I want to answer the question of how fast the suspect itself is going, which means I want to get dx dt alone. That is how fast is the suspect going, so I want to get that part alone. So now I'm back to algebra, and I just start moving my terms around. So dx dt by itself is going to be 40d plus 160p all over 2x. Now I can factor out something in common from the numerator. Factor out a 2, so that leaves me with 20d plus 80p over 2x, and then the 2's can reduce. So I would factor out a 2. I could factor out more than a 2, I understand that, but I'm only going to factor out a 2 because that's all that will reduce my denominator. Then I want to make sure to add units. Okay, and the unit, I look back to the original, and the unit for the numerator is measuring x, which is measuring the position of the suspect. That's measured in miles. And then the unit for time is being measured in hours, so this is miles per hour again. All right, how are we doing? You hanging in there? Yeah, Luke.
Just put MPH.
Yeah, MPH is fine. Okay. Yeah.
So, if it said the distance between them is decreasing at 20 miles an hour, then it would be negative 20.
Mm-hmm. Yeah. For the 80? Yeah, we added that because once we determined that the side was shrinking, the policeman's side is shrinking, then it has to have a negative rate. Okay. The policeman is going this way, which means his side is getting shorter and shorter and shorter and shorter as he's getting closer and closer and closer. The X side is getting longer because he's trying to get away. Okay, now, you notice that all of our answers so far still have letters in it. They still have variables in it, which means that the situation is still ongoing. It is still in motion. If you want to freeze frame the motion, if you want to stop the motion, that is when you finally put in a time value. If you put in a time value at the beginning, you have stopped the motion at the beginning, and your problem won't go anywhere. You need to let the problem work itself out through its motion, and then plug in your time value at the end. Then you freeze frame what's going on. All right, so the instant you specify all time, all motion stops. It's your freeze frame. All right, so you want to make sure you do this last. Again, it's the biggest mistake I see students doing is they plug in too soon. Okay, resist. You got to hold off. Okay, have patience. So here's an example of what you would do that. Okay, you're watching a hot air balloon, or maybe you're watching a drone, or you're watching something fly in the air. We have the word angle in here, so we know that we're going to be using something trig, and we've got a lot of numbers. Let's just get our model here. Okay, you are watching the balloon. That forms a right angle, but they're talking about an angle this time. So we're going to have theta put in down by the person because you were looking at the balloon. And then I'll call B for the balloon maybe. And let's call X for the person. You could call it whatever you want. I'll call X. Notice I didn't put any numbers anywhere on my picture. Save the numbers. Set up your trig. This is perfect because the B and the X are in the opposite and the adjacent position. So what trig is set up for that? Tan. This is going to be tan because it's opposite over adjacent. So I'm going to have the tan of the theta quantity is B over X. Set up your model, no numbers. Now put it in motion. Okay, have the thing start moving, which means use a derivative. So now, okay, this is a good review. What's the derivative of tangent? Okay, and remember, we're going to need the chain rule because there's parentheses. So we do what part of the chain rule first? The outside. And what do we do to the inside? Leave it alone. And then the derivative of the inside. Okay, so the derivative of the outside for tangent is secant squared. Maybe you haven't thought about that for a little bit. Leave the inside alone. Then the derivative of the inside, which is d theta dt. Okay, so that side is done. That's the rule, chain rule with trig. What rule do I need on the other side? Quotient rule. So x times db dt minus b times dx dt all over x squared. Okay, now we're going to freeze frame the situation and we're going to start putting our numbers in. Where does the 200 go? For all the x's. Okay, so the 200 is for all the x's. Okay, where does 10 degrees per minute go? D theta dt, and it says it's increasing, so I'll put in a positive 10. That's d theta dt. It was a degrees over minutes. Use the clue. Degrees is the d theta, minutes is the dt. Right? At the moment, the balloon is 100 meters high. Where do I put that? Okay, so I'll put that in for B. Thousand, sorry. So B is 1,000, X is 200. There must be something reading between the lines that I'm not there. I mean, these were the three obvious numbers. There's going to be stuff in there that's not obvious, that you're going to have to read through a little bit. Okay, so let's go back to thinking about what's moving in this situation. Is the balloon moving?
Yes.
Okay. Is the person moving?
No.
What does that tell you? That tells me that dx dt is 0. I can infer that because the person isn't standing still. The other thing I can infer is the secant of theta. This goes back to your geometry and your trig. What's the expression for the cosine of theta? Right? Adjacent over hypotenuse. Do I have the hypotenuse right now? Could I figure it out? Okay, using what? Pythagorean theorem. I could sure figure out a squared plus b squared equals c squared. So this is going to be 200 squared plus 1,000 squared, whatever that turns out to be. So what would, if cosine is adjacent over hypotenuse, what is secant? Hypotenuse over adjacent. And I want secant and I want it squared. So the secant is the square root of 200 squared plus 1,000 squared over 200. That's secant quantity squared. That is now secant squared. So that leaves me with only one thing that I don't know. That was the dB dt, which is what the question is asking me in the first place. Find the speed of the balloon. So that speed of the balloon is going to be dB dt. Then it's just a matter of cleaning up stuff. Using your calculator, simplifying, it'll all work out fine. The 0 is going to be great. Okay, the 0 is going to knock that out. You can reduce, you can do a whole lot of simplifying. What will the speed of the balloon be measured in? Once you get dB dt alone, and you've done your cross multiplying and all of that, what will the units be? Okay, the balloon units are going to be meters. And the time unit? Minutes. So meters per minute. Once I get my calculator. So if you have your calculator, you can do that multiplication. All right, last one. Here's a cone. Geometry first. Okay, a cone. 1/3 pi r squared h. What does pi r squared h sound like? Without the 1/3, what does it sound like? A cylinder, right. And a cone is a cylinder that comes to a point, and you put the geometry is you put a 1/3 in front of it. We want how fast, so we want dv dt. Am I going to need a quadruple product rule here? No, what am I going to need? Okay, because what's constant? A 1/3 and a pi. So I'll need h times 2r dr dt plus r squared times dh dt. Then I can go and start plugging in values. The 20 is okay, so then it becomes where do some of these numbers go? And I'm going to give you a clue that some of these numbers are extra. A cone is 20 centimeters with a radius of 5. The 20 doesn't go anywhere, and the 5 doesn't go anywhere. Because I want to know where the ice cream is. The ice cream is not at the top of the cone, okay? It's not 20 centimeters. The ice cream is down farther. In fact, what's the ice cream at?
0.
No, read it careful. 12. The ice cream is 12, not 20. So what's the purpose of the 20? Okay, so my ice cream is here. Let me just quick finish. If the ice cream is 12, but the whole thing is 20, did the radius stay the same? The radius started out at 5. Can you figure out what the new radius is using a little good old geometry? You should be able to. It's called cross multiplication. Okay? In other words, it started as 20 to 5. That's the ratio. We call that a 4-to-1 ratio. Now it's 12 to something. 12 to what? That would keep it to be 4 to 1. 3. Okay? It's going to be a radius of 3 to keep it as a 12 to 1 or a 4 to 1 ratio. Or just cross multiply and you can solve it. But the radius is now 3. That's what gets plugged into your formula, not the 12 and the 5. 20 and the 5, sorry. It's the 12 and the 3. Let's look at what other numbers we're going to be substituting. So we know that this is being filled, so that's going to be a positive value. And it's positive volume when you're filling something. And the positive volume is a rate of 3 cubic centimeters per second. So we're going to have positive 3 to go in for our dV dt. Then equals 1/3 pi, our h. Okay, so remember our h is 12. And then 2r, and we determined that our r was 3. Now dr dt, this is an interesting one. Okay, again, its value is not in the question anywhere, it's implied. So we need to go back to this idea here, okay? All right, so we've got, let me give us some space. So 20 to 5 was our height to radius ratio. And when we cross multiply, 20r equals 5h. And so r is 1/4 of h. So that's the ratio we were talking about. If r is 1/4 of h, you can do your derivative here and figure out what dr dt is. Dr dt is 1/4 of dh dt because the 1/4 is a constant. This is what's going to get plugged in for your dr dt right here. So again, it's not explicit in the question, it's implied because of the ratio, because both the height and the radius are changing. So we're going to plug in right here 1/4 of dh dt. Plus, okay, r squared, we've got 3 squared, and then dh dt. So we've got numbers plugged in for everything except this dh dt here and this dh dt here. And dh dt is how fast the depth, or h. So how fast dh dt, that's the question. And that's all that's left. We have values in for every single other expression. So to simplify, so we have 12 times 2 times 3 times 1/4. That simplifies to be 18 dh dt plus 9 dh dt. So that gives me 27 dh dt, which when I simplify that, I'll get 9 pi dh dt. So dh dt by itself is 3/9 pi, which is 1/3 pi, which is 0.106 approximately. And then we need our units. And so we need our unit for h, which is being measured in centimeters, and our unit for time, which is being measured in seconds.